hello everyone. Thank you very much for joining. My name is Gilani, PhD candidate at EPFL. I'm here to present our work about AC-driven Aptamer-Decorated Graphene FET for cortisol detection that we have done in collaboration with our lab, Xsensio startup, and SHU Hospital. First of all, I'm going to talk about the main motivation of the work, that why we chose cortisol as a target biomarker, and where we can find this cortisol, and how we are going to use the graphene FET and the lock-in amplifier to do the sensing, and how we are going to functionalize it and validate the functionalization, and then I will end up with the result and the conclusion. So the main reason that we chose cortisol is actually the stress. When the body is stressed, there are like 5 main hormones that are secreted in the body. That the main of them is the cortisol, that is also known as a stress hormone. So when the body is stressed, the hypothalamus gland in the brain started secreting CRH. CRH is stimulating pituitary gland to secreting ACTH, and ACTH activating the adrenal gland and starting secreting cortisol. So by measuring the cortisol, we can measure how stressed the body is. For the people who are suffering from chronic stress, there might be many problems, wide range of problems, health issues with different systems in the body, cardiovascular system, neural system, and others. And, but how we can diagnose the people who are suffering from chronic stress? For the normal body, the secretion of the cortisol is high in the morning and then it's starting to decrease. But for the people who are suffering from chronic stress, this rhythm of secretion of the cortisol is irregular, and in some people it's like always high, or it's like low in the morning and high at night. So by monitoring this cortisol level during the day, by either sequentially or real time, we can diagnose the people that are suffering from chronic stress. Of course, there are other interests for cortisol detection that can be other diseases like Cushing disease, Addison disease, or adrenal deficiency, or also other fancy applications like sport application or a performance evaluation for maybe like entertainment purposes or companies. But where we can find this cortisol? The cortisol actually can be found everywhere. From plasma to urine to saliva, sweat, everywhere. But the main biomarker that we selected is interstitial fluid. The main reason that we can benefit from selecting this biofluid is actually it is less contaminated compared to other biofluids. It's rich of free cortisols. The response time after the secretion of the cortisol is short enough. There is less low lag. And the pH level is relatively stable, and it is very accessible. Actually, it is industrial mature enough to say that it is point of care compatible. Our solution for this cortisol monitoring is developing a wearable device that can be mounted on the body and portable and convenient enough to extract the ISF or having access to the interstitial fluid and reaching it to the sensing part, which in our case is a graphene FET, and measuring the cortisol level during the day. And it is also not worth to say that it should be like at rest. It should be measured at rest to induce less stress to the body. But why we chose graphene FET for the sensing platform? Because it is very biocompatible. It can be, we can immobilize different bioreceptors from antibodies, aptamers, or even enzyme on top of that, either covalently or non-covalently, or with the pi-pi stacking. Also, it has exceptional electrical characteristics. It is offering a high surface area, and we can functionalize this recognition element very well aligned, that all of these aspects can increase the sensitivity of detection. And one of the other interesting thing about the graphene is that there is no oxide layer on top of it, so we can have more sensitivity. Also, These graphene FETs are very potentially good enough to be commercial. But, and also how we can use them as a sensing platform. So when we have the electrodes, we will have a double layers, including the aptamer or any recognition elements that we have. It can be modeled as the two elements of resistance or the capacitance. And when there is binding binding of with the this recognition, binding of the target biomolecule with the recognition element, we expect to have some changes in the capacitance. This capacitance can be measured using the GFETs. Also, to measure the capacitance, we use the lock-in amplifier, which is a very high sensitive tool for the very weak signals and with the high noise backgrounds to measure the amplitude and the phase. And we connect this lock-in amplifier to our GFETs. And lock-in amplifier is working like that. We introduce two signals. One signal that is coming from the sensing part and the reference, and we differentiate between two signals and amplify it and measuring the amplitude and the phase. In our case, the signal is connected to the gate of the GFET, liquid gate GFET, and the reference is connected to the drain. And we hope that using this configuration, we can, and also choosing the capacitance, we overcome the dBi length issue, and we have more signal to noise ratio. This is the optical picture of our GFET, the graphene FET. We use the array of the GFETs to ensure that the stability of the measurement. And thanks to these arrays, we can say that we can probably have a higher sensitivity and less power consumption. And also on the bottom, you can see the both diagram of the whole system. This both diagrams helps us to choose where we bias the frequency, and it should be in the highest magnitude, and where the phase is actually has a steep slope to have much more sensitivity to the changes of the phase. Why we choose the aptamer? The aptamers are actually chain of oligonucleotides that can fold in unique three-dimensional form. And when there is a binding, their structure can change. That we say it's like conformational change. And the aptamers are small enough, which makes them very interesting for the small molecule detection. And they have very high specificity and affinity, maybe compared to antibodies. They can be chemically synthesized, and they show much more stability compared to antibodies, and they can be produced very rapidly, and they are more convenient in terms of storage to antibodies. And to functionalize our graphene FETs with the aptamers, we use pyrene, which is an aromatic molecule that has a pi orbitals that can bind with the pi orbitals on the graphene. And these pyrenes are tagged with esters that can react with the amine part of the amine tag aptamers, and that's how we can immobilize our aptamers on top of the graphene. And one good thing about the aptamer is that not only they are binding, they also have the conformation change. So after this conformational change, we can induce voltage and current changes and also capacitance changes on the graphene. We also carefully validate the functionalization stack by stack. First layer was P-based pyrene that I just explained. We validate that with the Raman spectroscopy. We also optimize the solution that we use for this immobilization of the P-base. That, as you can see, there are the peaks shown in the Ramans after P-base immobilization, incubation. And we also validate the aptamer binding with the cortisol using AF and SNOW. And as you can see on the left, there is a picture before cortisol, and on the right there is a picture after the cortisol, and there is a change in the height all these experiments has been done in the 1xPBS, which is the buffer solution of our interest. And the other interesting thing that we have done to prove that there is actually conformation change of the aptamers after the binding is that is doing the CD assay, circular dichroism, that which is a very powerful assay to show and prove the structural change. These experiments also done in the 1xPBS. I have to also note that aptamers can be very sensitive to the ionic stress. That's why I am emphasizing on the 1xPBS. And you can see that after incubation with the cortisol, there is a change in the peak of the curve in the wavelengths, and proving that it is most likely there is a change in the structure of the aptamer. After all these validation of the functionalization, it's time to test our functionalized GFETs with the locking amplifier to see that if there is change in the phase after cortisol inhalation. We have done the experiment in 1xPBS. Each of these dots is 10 minutes incubation with the cortisol, with the different concentration of the cortisol, and the samples that we used was 15 microliter. And the experiment started with the buffer solution to reach to the stability in the baseline, and then in the baseline, and we started to the incubation with the different, starting from 1 picomolar to 1 macromolar, and we saw the sensitivity started from 1 nanomolar. We reached to the very interesting, excellent actually range of 1 nanomolar to 1 macromolar with this technique to consolidate the specificity of this sensing. We use also, we did the experiment with the non-specific to the with the sensor that is functionalized with the aptamer that is non-specific to the cortisol, and there has been no response, and you can see that the phase has been changed, which is the imagery. And as a conclusion, we successfully characterized the GFET with the lock-in amplifier. We successfully functionalize and validate this device, and we reached to sensitivity of 3.34 milliwatt per decay in a very good range of 1 nanomolar to 1 macromolar, which is the interesting range that we have in its interest of cortisol interstitial fluid. And all the experiment has been done in 1xPBS, that is make it more practical for the real usage. For later, we have to also do it in the real interstitial fluid and with the lower volume. And thank you for your attention. If there is any